Okay, so what happens if we cannot make sure that this uh, est- um, exploring starts assumption is correct, or that we can guarantee this? So one way to solve that is to use soft policies. And the idea is that to make sure that every action has a probability larger than zero to be selected, to be executed from each state. So here, one way to guarantee that probability different to zero is to use the Epsilon-soft policy. And the idea is to assign a probability to each of the actions. And this probability will be the epsilon defined for the Epsilon-soft. Like in the same way in epsilon greedy we define an epsilon probability of exploration. So you will assign that probability epsilon over the total number of actions available from that state. Okay, you will assign that probability to all of the actions except to the action that is the best one for that state. In the case of the best action for that state, you will assign 1 minus epsilon plus epsilon over the number of actions available from that state. So by doing this, we make sure that the probability over all the actions for a given state is a probability function. So if you sum all the probabilities, you will get 1. The sum of all the probabilities will be 1. So that's the way to avoid the exploring starts assumption by using an Epsilon-soft policy. And if you do that and you perform an algorithm that performs generalized policy iteration, then you will converge to the optimal policy. So one algorithm that we can implement to do that is called on-policy Monte Carlo control. So you will see some algorithms that say that the name is control. When you see an algorithm that it says that it's for control, then internally in the algorithm you will see in some part, like here, a way to define pi, or the probability of selecting an action. Okay, and when you see that it is on policy, it says that we have only one policy that we will be following when we are creating these episodes, and this same policy pi is the one that will update in each of the iterations. Later we will see off-policy Monte Carlo methods, and in off-policy, instead of having only one policy, we have two policies. One policy, which is the behavior policy, is the policy that we will follow to generate episodes, and we have a second policy that the second policy will contain the best actions for each of the states. So in this case we are talking about on policy Monte Carlo, so we will have only one policy, which we initialize here. We will initialize arbitrarily this policy, and in this case we are going to use an Epsilon-soft policy. And also we need to initialize the values for each pair of state and action. We can initialize them with 0, and also we need to generate a list for every pair of state and action. Initially these lists are empty. And in the main loop of the algorithm we have 3 steps. The first step is to generate an episode following the policy pi. Once we have the episode, for each pair of state and action, that appears in the episode, we will calculate the return, the total return, after the first occurrence of each of the pairs S and A. We will add that return to the list of returns for that pair SA, and then we will recalculate the average of the returns in order to update the Q value for that pair SA. In the third step, we need to update the policy. So the step B is the evaluation, policy evaluation, and step C is policy improvement. So we will, for each of the states that we found in the episode, we will select what is the action that has the largest Q value, and we will assign that action to this variable, the optimal action, and then we will update our Epsilon-soft policy in the same way we explained in the previous slide. So to the optimal action, big A star, we will assign the probability 1 minus epsilon plus epsilon over the total number of actions for that state. And to every other action, we will assign simply epsilon over the total number of actions for that state. So we will be generating episodes, performing the policy evaluation, so updating the Q values, and then the policy improvement, which is assigning the new probabilities in the Epsilon-soft according to this formula here. So this is an algorithm for Monte Carlo control in an on-policy approach and with only first visit averages. Okay. So Monte Carlo has several advantages over dynamic programming. We can summarize them here. So Monte Carlo can learn directly from interaction with the environment. So we don't need to have a model of the environment. We can simply interact with the environment and learn from this. So we don't need a full model. If we have it, then we can use it, but we don't need to have a model. No need to learn about all states because we don't do bootstrapping. So we can simply generate episodes and learn from the experiences with the states that appear in those episodes. When we don't do estimations of estimations, we simply compute averages of real returns. It is less harmed by violating Markov property. Remember, the Markov property tells you that the probability of selecting the next state and the next action depends only on the current state, not in the history of transitions of states. And since in Monte Carlo we are learning from direct interaction with the environment, we are learning from real experience, then if this Markov property is not really valid for our specific NDP, that is not too much problem because we are not computing probabilities of transitions. We are actually performing actions in the environment and getting real experience. And Monte Carlo methods provide an alternate policy evaluation process. So we can evaluate policy using dynamic programming. This is another way to perform policy evaluation using real experience. And one issue to watch for in the case of Monte Carlo is that we need to keep sufficient exploration. Remember that the first approach, the first algorithm that we studied in Monte Carlo make the assumption of exploring starts. So in order to converge, that algorithm requires that all the pairs of states and actions has the same probability to be the initial state and action. But if that cannot be guaranteed, then we can use, for example, on policy Monte Carlo with the help of soft policies. And this is another way to guarantee that we will find the optimal policy. Now, As I said before, there is another approach of applying Monte Carlo methods. That's the off-policy method. In off-policy, we have two policies. One policy that we follow to generate episodes, and one policy that we will use to store the knowledge that we learn. So in this case, we learn the value of the target policy pi from experience due to another policy, a behavior policy that we call here B, policy B. For example, pi is the greedy policy and ultimately the optimal policy, while we will have some mu policy as an exploratory policy. For example, this mu policy involves following an Epsilon-soft policy. In general, we only require coverage. This is a very important concept. Coverage means that if B generates some episode, that episode can be also generated by following policy pi. Okay, so we need to guarantee that. So mathematically, we say that the probability that some action is selected given the current state S, if that probability is going to be larger than 0 for every state and action, for every S and A, at which our behavior policy has also a probability different to 0. So it means that if you move around following the actions suggested by the behavior policy B, all the transitions that you can generate by following this policy, all these transitions should be also generated or be possible to be generated by following the policy, the target policy pi. So that's what we call coverage. So that is one condition. Now, since we are generating episodes, here we will be generating episodes following a policy B, but we will be updating a second policy pi in order to compute correctly the probabilities of these transitions in the episodes that we will generate. We need to calculate what we call the importance sampling. So this is a weight each return will have by multiplying the ratio of the probabilities of the trajectory under the two policies. So we will generate episodes. We need these episodes to get the final return, but this final return will be weighted by this importance sampling, which we will see is defined as the ratio of the probabilities of these trajectories, of these episodes. So the probability of the rest of the trajectory after some state t under the policy pi can be computed as the probability that you will have the starting in state t, you will have the action t, and then you will visit the state t plus 1. In that state you will get or you will execute action a t plus 1 and so on until you reach the terminal state. All this sequence based on the fact that you started in state t. Okay, and these sequences were generated using a policy pi. So this is the probability of that sequence. To compute that or to calculate that probability, you need to calculate the probability that you will select action AT in state ST and the probability that you will transition from state T to state T plus 1 given the execution of action AT times the probability that you will select action T plus 1 in state T plus 1 and the probability that you will going to transition to that state ST plus 2 given that you are currently in state ST plus 1 and so on until you reach the final state. So this is the way you can calculate, given some policy pi and the transition probability of the environment, how you can go from some state T to some state terminal state big T. Of course, in Monte Carlo we are assuming that we don't know this transition probability. Okay, we are assuming that we can simply perform actions following some policy pi in this case and move from one state to the other until we reach the terminal state. But in this analysis, we can assume that this is the way we can calculate the probability. This is going to be or can be expressed like this product from k equals t to t big T minus 1 of the probability given by the policy and the probability given by the transition function. Okay, this is in case of policy pi. We can calculate the same for policy B, for the behavior policy. And the important sampling that we were talking about will be the ratio of the probability pi over the probability of behavior. And since in both cases we have these transition probabilities, we can cancel out the probabilities. And this is very good because we are in Monte Carlo, as I said, and we assume that we don't have these probabilities. So in the end, this important sampling concept will be the ratio of only the probabilities of selecting actions based on the states following policy in pi, the target policy, over the policy, the behavior policy. And this will be computed for all the transitions and all the actions that you will find in an episode. So this number here is the important sampling ratio, and we are going to use that number to weight the final return. So given 2 episodes, and each of these episodes having a return, some episodes will be more probable to happen than others based on this number for those specific episodes. And here we are simply saying that this is a probability distribution. So if we compute this ratio for every possible action given a state, in the end we will see that this corresponds to the sum of all the probabilities of selecting actions in that state, and this should be 1. So this is a probability distribution. So how we can use this important sampling? The first thing is that each of the episodes will be, let's say, concatenated. So the time step increase across episode boundaries. So we will create episodes, and when we reach the final state or terminal state, and we start the next episode will start in time step, in this case 10. You will continue following that episode, and here we are assuming that in time step 25 we reached the terminal state, and we started a new episode in time step 26. So we will keep increasing the time step across episodes, but we need to keep track of these single episodes, and the elements that we need to keep track especially are, for example, this stylized t, and this is a set of all the starting times, all the time steps in which we initialized an episode. So we visited for the first time an state given an episode. So in this case we are saying that some state S was visited the first time in time step 4 and also in time step 20, and each of these starting times will have a terminal state. So when we visited the state 4, we ended or we reached the terminal state in time step 9. When we visited the state S in time step 20, we reached the terminal state in time step 25. Okay, so we need to keep track or store this set for every state in our MDP. So by counting this, we can then calculate the average of the returns, as we are doing in Monte Carlo. Remember, we need to consider how many times we visit the states in different episodes, so we can recalculate the average of the returns. So that's exactly what we are going to do here. The only difference will be that we will consider this importance sampling. And the importance sampling that I explained in the previous slide can be considered in two ways. One way is used ordinary importance sampling. In this ordinary importance sampling, we will multiply this row from time step t till time step t of small t minus 1 is this sampling here. Sampling probability is going to be a weight that will multiply the final return. And in the ordinary application, we will divide this number by the number of times that we visited the state S in all the different episodes that we generated, which is in this case, in this example, is going to be 2, because we visited that state in time step 4 and also in time step 20. So this, in the ordinary importance sampling, we will divide this by 2. But in the weighted importance sampling, we will divide it not by the number of times that we visited that state, but we will divide it by the same number here. And usually this weighted importance sampling, when you apply that in the algorithm, provides a more stable estimation of the value function. So it is preferred the weighted importance sampling over the ordinary importance sampling. Ordinary importance sampling introduces more variance, especially during the initial parts of the algorithm. So we will prefer the weighted importance sampling implementation of this. So we will see two algorithms that use this importance sampling. The first one is for prediction. So in this case, we will be estimating Q values for every pair of state and action. We need to initialize that table or that function for each combination of state and action. And we will use a temporary variable here, which is C. And we need to initialize this for every combination of state and action. Then in the algorithm, we will need to define a behavior policy. We need to make sure that that behavior policy has a coverage over the target policy pi. And then we generate our first episode using that policy B. So here we have an example of generating this episode. And then we initialize variable G, which will contain the return, and some auxiliary variable W that will contain, basically, as you can see here, the raw function, or the ratio between the probability of the target policy and the probability of the behavior policy. So we will run a loop from t equal t plus t minus 1. So we will initialize t from the penultimate time step, so the time step before reaching the terminal state, and we will decrease that t down to 0. So we will generate our episodes, and then we will move this small t from this position here to the left until we reach the state 0. And every time we do that, we will update G, which initially is 0, by gamma, which, if you remember, is the discount factor that could take values between 0 and 1, plus the reward that we got in time step t plus 1. Okay, once we have calculated G, we continue and calculate or update the value of C for our pair S, T, and AT. And we will simply add what we have initially, which initially is 0 here. We will add a W. W initially is 1. Then we update Q. Q will have what we have currently in Q, plus W over the Z value times the difference between the final return and the current Q. So this expression here is an incremental way to compute, let me go back, to compute this expression here. Okay, instead of storing in a list all the visited states and the resulting total returns, we can incrementally compute this value here, and that's what we are doing in this rule. Once we have updated Q, we update W, which W will be the probability of going or selecting action AT in state ST over the same probability but from the behavioral policy. If you happen to get a W equal to 0, then you go out this loop. And that's what you need to do. You need to every time you generate an episode using our behavioral policy, we need to go from the last or the penultimate state to the first one, updating incrementally the Q values and updating the W's, which are the weights. And this W, remember, is how probable, or what is the probability of really generating this episode. And if we can generate that episode, then we can multiply the final return. Finally, a second version of this algorithm is an algorithm for control. So the only difference between this algorithm and the previous one is that we will keep a specific variable for storing what is the best action for every single state. So the only difference in this algorithm then is that we will have to update also every time we evaluate our policy, our Q function. We need to update or we need to improve the policy improvement of the target policy. So we will store here what is the action that maximizes or has the maximum Q value for that state. And that's all we have to do. This is the only difference. We keep updating the returns, this temporary variable C, the update of the Q value in an incremental way, and we update the policy. If the action that we select is different than the actions suggested by the policy, then we exit this loop and we simply then update the W. In this case it's a bit different. We just have to divide 1 over the behavior. And this is a second way, or second version of policy Monte Carlo, in this case maintaining a special variable for the policy. So the target policy is greedy and deterministic, because here we are always specifying for each state what is the best action, and the behavioral policy is soft, typically epsilon greedy. So the way we generate this is using the behavior policy, and we need to specify this as a soft policy. So this B policy, in this case, we need to specify it as we saw previously with Epsilon-soft. So as you can see, if we compare dynamic programming algorithms with Monte Carlo algorithms, in dynamic programming we need the transition probabilities from one state to the other, and we need to compute from each state what are the possible paths that we can follow according to these probabilities. In this case, we assume that we don't have this transition probability, so we need to generate this transition. So we need to really interact with the environment, performing actions, and learning from the final return that we get once we have reached the final or terminal state. So these methods do not bootstrap, so we learn from averages of real returns, and we can implement it following two main approaches: on policy, using only one policy, or off policy. So okay guys, this has been then Monte Carlo methods. These are the basic algorithms, and I hope this is useful. Thank you, and talk to you later. Bye.